Right, I can talk again about the Natural History Museum. So now that we are recording, I'm sorry, the online people, I'm going to talk a little bit about the Natural History Museum again. So it houses 80 million specimens. We have 300 scientists on site and 9,000 science-based visits per year from 100 different countries, researchers from 100 different countries. And we also publish over 700 articles per year in collaboration with other international institutes. Oh, and my name is Dr. Ana Santos, and I'm a research fellow in geomicrobiology at the Natural History Museum. I'm sure all of you must have heard this quote before. If you can't grow it, we'll have to mine it. And that is still true, and it will be true for a long while. If we can take a few lessons from the COP26, here are 9 lessons, and I highlighted 4 of them, 3 in green and 1 in red. One of them is accelerated the transition to clear energy, ensuring sustainable land use, and driving towards zero emission transport. And one that is also very important is progressing meaningful participation by women and girls. And what we need, and we know about this, with the transition to a clear energy, our digital and transport transition to electric cars, to mobile phones, laptops, everything is electronic. We're going to need to mine metals to meet the demand for all of these technologies that advance every day, and we don't have enough metals to keep the demand. And of course, to meet that net zero carbon emissions by 2050, we are going to have to mine a lot. Here, just to illustrate what I'm talking about, the demand for metals, and it's not just in terms of quantity, it's also the variety of metals, because now we need more metals and other elements that we didn't need 200 years ago. And here, just as an example, by 2050, we are going to have to produce 500% more graphite, lithium, and cobalt to complete our energy transition. But what about recycling? Everyone talks about recycling. Unfortunately, at this moment, recycling is still not enough. In the graph on the left-hand side, you can see the orange bars represent the percentage of commodity recycled at the end of life, and the blue is the percentage of current demand satisfied by recycling. So you can see the first very big discrepancy, that is cobalt. We only recycle half of what we need. Where are we going to get the other half? We are going to have to mine. But how can we mine in a way that is not as harmful to the environment, that will help us meeting the demand? And we're going to use less energy, and a process that we can open the possibilities for low-grade ores and for wastes. And just as something to bear in mind, the list of critical raw materials keeps on growing. When they launched this list, when they released the list in 2011, we had 14 elements, 14 critical raw materials. Then, and they review this every 3 years. In 2014, it went up to 20. 2017 is 27. 2021, 30. And then 2024 is the next review, and it will probably increase. So again, the variety of metals and elements that we need to make this transition. Not only how much more we are going to mine is what is important here is the amount of waste we are producing at the same time. Over 90% of what is excavated is considered waste. And the mining sector consumes 5 to 6% of the energy produced globally. That is for transportation, for grinding, for keeping the smelters very high temperatures. And not only that, the flotation process, which is used in pyrometallurgical techniques today, and is widely used, generates per year 700 million tons of tailings around the world. This is all the waste that we can't use, or we didn't look into using it before in a more efficient way, because in the past we didn't have the technology, but now we are getting closer to getting that technology. Not only that, having these tailings and also the waste rocks exposed to air and water in the environment, that triggers the generation of acid mine drainage. So we have the oxygen, water, and that gives the best conditions for ion oxidizing microorganisms to catalyze the oxidation of sulfide minerals with the generation of acid, and generating acid and also releasing metals into solution. And that can be very detrimental, is an environmental liability. And with the tailings, there are different ways that you can store tailings. We have the tailings storage facilities, and they are usually in ponds, in enormous ponds. And we hear every now and again an incident of one of the dams that collapsed. And unfortunately, there will be more, because we still have way too much waste, and the tailings management still needs to keep up. But now I'm going to move into something more positive. I'll give you a few examples, and I will explain what biomining means. It's an area of biotechnology that uses microorganisms to extract and recover metals from ores, mineral wastes, and mineral concentrates and waste materials. And within biomining, we have 3 different areas. One of them is bioleaching, in which the destruction of the mineral leads to the target metal to be in solution, to be solubilized. Biooxidation, the metal becomes more accessible to chemical extraction, but remains in insoluble form. And that happens mostly with refractory gold. And biomineralisation is pretty much the opposite of the other 2. The first 2, you want to get metals in solution. The second one, you want to precipitate those metals out. I will touch very briefly on the history of biomining. In the late 40s, the first bacterium, a novel bacterium, was isolated from water draining a coal mine that was able to oxidize both iron and sulfur at low pH. Back then, it was named Thiobacillus peroxidans, and a few years ago, quite a few years ago, how many years ago, it was renamed, and it's now called Acidithiobacillus peroxidans. Acidi, it lives in acid. Thio, it's got sulfur metabolism. Bacillus, because of the shape of the bacterium. And ferrooxidans is oxidizes iron. So usually the name of these microorganisms is related to what they are able to do, so then it's easier to remember when we need to memorize these enormous names. This one, Acidithiobacillus peroxidans, has been one of the most widely studied of all bacteria outside of those of medical importance. So people like this one, people want to study this. In the early 50s, other similar bacteria were isolated as well, because now the scientists back then knew what they were looking for. And they also found that these bacteria were able to solubilize pyrite. But the thing is, in the 40s, what happened is they isolated the bacterium, but these processes were happening ages before the scientists found these bacteria in the water. And one good example is the in situ biomining. In this copper mine in Mynydd Paris in North Wales, the shafts after the mine was closed, they were allowed to flood periodically, and then they would drain that water, and then they managed to recover copper from that water, even over 100 years after the mine activities ended. But how does it actually work? How does the bacteria do that? There are some species of these microorganisms. They're called lithotrophic microorganisms, and they basically eat rocks. And they can selectively degrade sulfide minerals in low pH liquors. And here is an example of a mineral before it was subjected to biological attack. And then the second figure here shows how the mineral looked like after. And you can see where is my cursor? A lot more porous than the other one. And here's just to illustrate how they look like, how the bacteria look like. And you can associate the bio-leached mineral to Swiss cheese, because it looks a little bit like that after the attack. But why do they do that? They are doing this. They are attacking these minerals because they are after the energy that is locked up in this in the reduced forms of the sulfur and the iron, the sulfide and the ferrous ion in this type of minerals. And the acidophilic ion and sulfur oxidizing prokaryotes, they accelerate this oxidative dissolution. So the presence of bacteria there increases the kinetics by orders of magnitude. They do it a lot quicker than we could do chemically. There are, since the discovery of the first bacterium, there are many mineral bioprocessing technologies applied commercially. So in the 60s, the first big scale operation used run-of-mines dumps in New Mexico. And here you can see the big dumps, and they have aeration on top. And no, sorry, not aeration. They percolate through acidic solutions, and then the PLS is recovered at the bottom. And in the 80s, they made it a bit more controlled. So they use heap leaching, which is the same concept, but is more engineered. So you have more control of what's going on. And the size of the particles are also monitored here, while in the dumps is whatever size it was left. In the 80s, they started a different type of technology using stirred tanks. And these big tanks here were primarily used for gold recovery, because it's a much more expensive setup than the other two. So of course the method that you are recovering needs to pay for the process. Today, the numbers today are the following. Around 15% of the global copper production come from biotechnological processes, 6% of gold, and smaller percentages of other metals. I'll go into the mechanism very quickly. I'm not going to go really deep into this, but that will just help me explaining the case study afterwards. So the oxidative bioleaching is used for reduced ores, sulfidic ores. And the key reaction there is ion oxidation, so the bacterium can get energy from that reaction. Acidity in this case is often generated, so that is the problem with acid mine drainage when the bacteria are processing this material, they are generating acid. The bacteria need something to eat, and in this case the electron donor is already present in the mineral, so you don't need to add anything. The electron acceptor is oxygen, and what that means is that you need the system to be aerated. And then the pregnant leaching solution that it's generated in this process is oxidized. Now, the complete opposite is the reductive bioleaching, and that is for oxidized ores, which is a completely different type of ore. And the reaction here is ion reduction. So we want to go from ferric to ferrous ion. Acidity is consumed, and an additional electron donor is needed in this case, because the bacteria, they are able to get energy from what is ion 2 to ion 3, but they can't do if it's ion 3 to ion 2, the different oxidation states. So you do need to feed them something to get them going. The pregnant leaching solution generated is reduced, and that means that the reductive bioleaching in most cases needed to be carried out under anaerobic conditions without oxygen. What is interesting about these two types of bioleaching is that it's the same group of microorganisms are doing these two things. The difference here is if you give them oxygen, they will do one thing. If you take the oxygen away, they will do a completely different thing. So you need to know what type of ore or waste that you've got to know which type of bioleaching to apply. Now I'll go through the case studies, which is a bit more interesting than all of the mechanisms and the science, and then just to show that it does work. So this is the one of the examples of oxidative bioleaching used to reprocess sulfidic tailings. So the story behind this was in late 50s, there was a mine operation to recover copper from Kasisi in Uganda. So the mine closed in 1982, leaving behind over 1 million tons of cobalt-rich tailings. The tailings contained 80% pyrite and 1.4% cobalt. But they were interested in copper. They didn't care about the cobalt back then. But the problem, like I said before, is oxygen and rain in a very reactive material. Acid mine drainage started being produced. The runoff was going straight to a reservoir in the middle of the Queen's Elizabeth Park in Uganda, and they're also destroying everything in the way. So what they decided, what BRGM, the French Geological Survey, decided to do was to start this project to see if they could eliminate that environmental issue. When they looked at the tailings and then they saw that the tailings contained 1.4% cobalt, and that's now 1995, cobalt is a lot more important now than it was before, and this concentration, it was higher than what mining companies were digging out of the ground to process. So then when they looked at it, this is the perfect opportunity. So in 1995, they set up the bioleaching in stirred tanks. And we use stirred tanks if the metal you're going to recover is going to pay for the process. And in this case, cobalt would do that. And in 2013, they closed the operations, they ceased operations because all of the tailings had been reprocessed. So that acid mine drainage was remediated, and there was no more environmental issue with that type of waste. And they produced over 600 tons of cobalt per year during the years of operation, with a generation of cathode cobalt with 99.9% pure. This is an industrial scale application, but now the second example is a lab scale, and that is most of the studies. They will select different tailings and apply different techniques. So this is just an example of a two-stage bioprocess using tailings from a copper mine in Spain that was generating 1.5 million tons per year. And that tailings contained 0.7% of copper and a little bit of silver and zinc as well. And so this work was carried out at Bangor University, led by Professor Barry Johnson. And the idea here was to bioleach the tailings using microorganisms, testing different temperatures, different pH values, and then once we had the pregnant leaching solution full of copper, the second stage was to selectively precipitate the copper in that water. So here we have bioleaching plus biomineralisation in one system. So here's just a picture of how the reactors look like in the lab. So the first one is for the bioleaching of the tailings, and the second one is the selective precipitation of copper. I'll go a little bit more into how you selective precipitate metals in a little bit. Now, moving to reductive bioleaching. We talked about oxidative.
You better go and get yourself ready, love.
That's what I've exactly just said as I came in.
And now we are going to talk more about reductive bioleaching. And it's also known as biomining in reverse gear because it does the opposite of the traditional biomining. Can you please, everyone that is online, can you please just mute your microphone? Thank you. Right, so reductive bioleaching. It's used for oxidized minerals, and in this case, it's mostly used for laterite deposits, in laterite deposits. Here there is like a very simple, very simplified schematic of the profile of a laterite deposit. So the saprolite layer, which is the layer that contains more nickel, is processed nowadays using pyrometallurgy. The limonite layer, because of the concentration of nickel being quite low, is often stockpiled because it's not good enough for pyrometallurgy. So then there is this waste just sat in a corner. So how can we use the microorganisms to process that material that is considered waste? So we use the same group of microorganisms, but now you can see here the first reactor, when I mentioned that in this case, they can't get the food that they need to catalyze the process. You need to give them some food. And one of the electron donors that you can use is sulfur. This is the reactor showing the microorganisms growing with sulfur. That's why it's yellow. And then it becomes orange like that once you add the limonitic laterite into the reactor. So once you do that, what is happening inside of that reactor is the reduction of the ferrous oxide phases, the iron oxide phases. When that happens, that consumes a lot of acid, but that also releases iron 2, ferrous iron. And that ferrous iron is used to attack chemically. Now, chemically, the iron 2 generated biologically is used to attack another mineral that usually contains cobalt. This is part of a project funded by the European Union, and they were looking of different ways to recover cobalt from wastes, and also from batteries and electronic wastes. So here, the focus was to recover as much cobalt as we could, but also taking some of the nickel if we could as well. And then after this process, you end up with a PLS that looks more or less like that. And then you can apply the biomineralisation, so you can precipitate the metals from the solution. The reductive bioleaching using limonitic laterites has not yet reached industrial scale, but we do have an example of a pilot study carried out in Piauí in Brazil in association with the mining company Brazilian Nickel. What they do in this mine in Brazilian Nickel, they process the saprolite layer, the layer with lots of nickel, using sulfuric acid, one of the hydrometallurgical techniques. So here you can see the guys from Brazil mixing the sulfur, that is what the bacteria needs, with the material, and then they packed that into these different columns, and then they sealed those columns because this process cannot have oxygen. So after a few days, after a couple of weeks, we ended up with this beautiful green solution full of nickel, all biologically generated. Now moving to bioremediation of mine water. So one type of waste that the mining sector generates is the tailings and the waste rocks, but there is also the mine water generated within the mine site. And to come up with ways of remediating the water, we had to go out and learn from nature and adapt natural systems that showed us that attenuation was happening. And this is a very, very good example, and I love to talk about that. This Cantarera site is a copper mine in Spain, and you can see here the open pit is just on the other side of that mountain, but then there is this channel, these two channels here with acidic mine water, and I don't know if you can see from there, but it's green. The two channels, the top layer of these two channels are green, and then there's water on top of that. And when we disturbed part of this channel, we noticed that underneath there was a particularly dark sediment, and we could also detect hydrogen sulfide being produced. That's all happening in nature. The only thing I did was to put the trowel there and check underneath. So what's happening there is a symbiotic relationship between these microorganisms. So like I said before, some of these microorganisms, they need some specific food. And these guys here, they need organic carbon. In a mine site, you don't get organic carbon. It's just metals and acids and water. There is no organic carbon. So you would have, in a confined environment, in a reactor, you would have to provide that. But how were they getting that from nature? And we can see here that the first layer is algae. And what algae do? They photosynthesize. They use CO2 and generate organic carbon. The organic carbon is then released into that water. The bacteria, the layer underneath, catch that, and then they can do the process that they need to do. And this is all just for energy. They are not doing this because we want the metals. They are doing this, and they've been doing this for millions of years. It's just us harnessing their metabolism and using them in our favor. So we thought then, can we do this in the lab? Can we turn this natural system into a confined, controlled system? And yes, we can. And this was my PhD thesis, where I looked into remediating acid mine drainage that contains a lot of copper from a copper mine in Brazil. And you can see the picture here, that the color of the water is very nice and blue. It looks quite beautiful, but that's copper. Yes, that's just copper, and that's very harmful, not only for the environment, but for us as well. So is that a way that we can process that water using the natural system? So what we did here was to get a bioreactor and mimic what was happening in nature. So this is the black sediment, basically, with all the bacteria, and this group of bacteria is called sulfate-reducing bacteria. They are the ones that generate hydrogen sulfide. Hydrogen sulfide, in the presence of metals with a +2 valence, they get together and precipitate. So, and that's why the sediment was black. There was less copper in the water, and there was lots of copper in the sediment. So can we do the same? So here we attached to this reactor an offline vessel, and this offline vessel was used, the hydrogen sulfide generated in this bioreactor was delivered to the offline vessel in gas form. And in this vessel, there was the mine water. The color is pretty much the same, but that was made up in the lab. That's not the water from Brazil. We got the composition and we just recreated it in the lab. And you can see that over time, the color of the solution changes, and then there is a formation of precipitate that in the end, I just filtered, and it gave me this beautiful precipitate, which is pure copper sulfide. So the copper present in that water was removed and recovered. Another thing about mine waters, they contain high concentration of sulfate, and sulfate is also very bad. And we're using biosulfidogenesis, which is the generation of sulfide biologically, biosulfidogenesis. You can also lower the concentrations of sulfate at the same time they are removing metals from the water. So it is a win-win situation here. Oxidative biomineralisation, this is specifically for cases where there is lots of iron in the water. So then you use the oxidative process. You need to oxidize all of the iron from iron 2 to iron 3, and then you can precipitate the iron and remove the iron from the water. This is used widely because most acid mine drainage, they will contain quite a lot of iron. But these two examples, they show only the removal and recovery of one metal. But in the field, in the mine site, the mine water doesn't contain just one metal. It contains all of the metals that were in the ore body before. So the beauty of this integrated system is that you, having the composition of the mine water, you can play about and use these modular systems to eliminate one by one or reduce the concentration of these metals in the water, cleaning up the water. And this was a very, very nice project also carried out at Bagger University, using mine water from Sweden, from a zinc mine in Sweden. And this mine water contained significant amount of zinc, but also arsenic, cadmium, copper, aluminium, manganese, and iron. Arsenic, we all know if you say this word, everybody goes, oh, that can't be good. And so we had to remove the arsenic from the water before the beginning of the process. And the way that this was done was very clever. So I said before, the ion oxidation and precipitation happens during oxidative bioleaching with the production of iron minerals, and one of them is schwertmanite. Schwertmanite is a positively charged mineral. Arsenic in this form, arsenic 5 in this form, can absorb onto the surface of schwertmanite and then is removed from solution. So here we produced a product that was also used to remove the arsenic from the water. So and schwertmanite can also be used in ceramics, in paint. So there are other secondary applications to it as well. Once we got rid of the arsenic and the iron in that water, then we used the biosulfidogenesis, the generation of hydrogen sulfide by bacteria, to precipitate all the other metals. And here we were just playing with pH values and solubility product. So with different pHs, each metal will precipitate selectively. So if you can control pH, you can get metals separate. Some of them have their properties are very similar, so it is a lot more difficult to separate, but then that is just 2, not 6. So that was a very, very nice integrated system, and usually out there, that's how it's going to be applied. Unless you want just one of the metals, but because nowadays we need so many different ones, you might as well just go and process everything and recover as much as you can. This is just the industrial scale process, and there are two. One is the thiopack process based on sulfate reduction for zinc recovery. And there is the biosulfide process based on sulfur reduction for copper recovery. So these are, most of these experiments have been done in the lab. There are some pilot scales, and these are two examples of industrial scale applications. So now the question that I always get after my talks is, why has not biomining totally transformed the mining industry? It sounds amazing. Why people not use it more? It's still a niche technology. And there are a few drawbacks. The process is slower. It can take days, but in heap leaching can take up to 5 years. A mining company is not willing to wait 5 years. If you compare that to pyrometallurgy and hydrometallurgy, time is money. Those are the two. You get the product a lot quicker. So that's one drawback. There's also mistrust in biotechnologies within mining industry. I'm not really sure if that's the thing. They are reluctant not to use what they've invested in. So you go there, you build a big smelter that costs you a lot of money. You're going to use that as much as you can to get your money back. So that's another drawback. There were, of course, a few situations where biomining didn't go as planned, and then it didn't work, and also in a few cases generated environmental issues. So that's also, you're going to think twice, so you don't want that to happen. And one other drawback is that the biomining, sometimes the green credentials is overplayed. Oh, biomining is all green. Not really, because we still, in case of biomining applied to ores, you still need to dig the ore out of the ground. You still need to grind it. You're going to still consume a lot of energy to do that. But if we're talking about reprocessing the waste that is already there, all once processed in a pile or in a pond waiting, then the green credentials of biomining go up. But luckily, things are changing, and this is my last slide. We have a lot to do before 2050, and we need new ways to mine. We will keep mining, but we just need different ways to mine. We need bioprocesses or chemical processes that are less impactful and they are net positive. Wastes should not be considered wastes anymore. They should be considered as secondary resources, because if you go back to legacy mines now, the waste generated from legacy mines, and you're going to look at that tailing, that will contain many metals that we need for our energy transition today. Responsible mining has to be inherently reconstructive. We don't want to see scars on the landscape. We want, after the mine finishes, we want to see a green field with trees again. So that is another way that we want less of this and more of this. And we do need to develop a cradle-to-cradle approach to mining, not a cradle-to-grave. And with that, I would like to thank you all, and I'm happy to answer any questions.